Hello, this is Mr. Stansbury. I'm going to take you through the 14 G notes on compound events. At the end of this, you should be able to say, I can distinguish between dependent and independent compound events and find the probability of the events. Okay, so let's talk about independent and dependent events. Okay, independent events are events where the occurrence of one of the events does not affect the occurrence of the other event. For example, flipping a coin. Every time you flip a coin, there's doesn't matter what happens on the first flip or the second flip or the third flip or whatever. The next flip will always have a 50-50 chance of getting heads or tails. All right. Actually, I guess officially it would be a 100% chance of getting heads or tails, but 50% chance heads, 50% chance tails. Rolling a die twice, again, doesn't matter what happens on the first one as to what will happen on the second one. And then picking two odd numbered tickets from a hat with replacement, meaning that you would have replaced the first ticket. So you take the ticket out, see if it's odd, put the ticket back in, and pick another one out. Okay, so those are all independent events. Dependent events are events where the occurrence of one of the events does affect the occurrence of the other event. So, for example, picking two odd numbered tickets from a hat without replacing them. So you take the ticket out and then you pull another ticket out. Kind of like picking two face cards from a deck of cards without replacing the cards as you pick. Okay, so those would be considered dependent events. All right, so let's take a look at some of this stuff here. So a coin and a six-sided die are tossed simultaneously to determine the probability of getting a head and a 3. Okay, so again, on the last set of notes, we went through and we made like a 3D, not a 3D, sorry, a two-dimensional grid, right? So we use grids to find the probabilities, but on this one here, we can go through and make this a little bit easier. So the big key word on this here is and. That means they both have to happen. So the probability of getting heads is 1 out of 2. Okay? And the probability of getting a 3 on a six-sided die is 1 out of 6. So what you do is you take those two probabilities, since it's and, you multiply those two things together, okay, to get us 1 out of 12, or I think it was 8.3. Yeah, let's see, clear 1 divided by 12 gives us 8.3%. Okay, so these would be considered independent events because, again, it doesn't matter what happens on the coin as to what you're going to roll on the die. Okay, so pretty much all dice and coins are all independent events. All right, let's take a look here at example 11, page 472. A cage contains 4 wolverines and 2 honey badgers. Supposedly 2 of the most ferocious animals on Earth. Don't be afraid. It's okay. 2 of them are randomly selected from the cage without replacement. Find the probability that both are wolverines, and the first is a wolverine and the second is a honey badger. So on this one, you're assuming that you're not putting them back as you draw them. So you're gonna take out 2 of them are randomly selected from the cage. So probability that the first one chosen is a wolverine is, let's see, there's 4 wolverines, 2 honey badgers, so there's 4 wolverines out of 6 total animals in there, right? So probability of getting your first wolverine, 4 out of 6. Now your probability of your second wolverine, because you already have 1 out, is now there are 3 wolverines left out of 5 total animals left in the cage. So that's going to give us 12. 4 times 3 is 12. 6 times 5 is 30. So that's 12 30ths. Both of those are divisible by what? 6? 2/5 or 40%. So either one of those would work. Okay? So what is the probability that the first is a wolverine and the second is a honey badger? So wolverine, again, we already know is 4 out of 6. And then we're going to multiply because we've got and the second is a honey badger. So there are After you take the one wolverine out, there are 5 animals left, and 2 of those animals are honey badgers. So that would give us 8 out of 30. Let's see, both of those are divisible by, I guess it's just 2, so that's going to leave us 4/15. Or, let's see, 4 divided by 15 gives us 26.7%. All right. Okay. So that's that. Let's take a quick video break, shall we?
Sweet potato fries.
Chicken in a basket!
Son of a Sacagawea. Break. Oh, John Philip Sousa. Oh, my God. It is a park. Away from the kids. Aim for the lake.
Sorry, I just love Phil Dunphy from Modern Family. He kills me every time. Anyway, let's get back. We have one last example. Example 12 from page 472. Hat contains tickets with the numbers 1 to 20 in it. If 3 tickets are drawn from the hat without replacement, so again, if it's without replacement, that's pretty much going to be dependent events, because what happens on the first one is going to depend on what happens on the second one, just like with the Wolverine and Honey Badger question. Okay, determine the probability that all are prime numbers. So, well, we know that we have 20 tickets in there, and then we got to come up with all the prime numbers. So let's see, 1 is a special number. Let's see, 2, 3, 5, 7. Let's see, 8 and 9 aren't. 10 isn't. 11 is. 12's not. 13. No 14 or 15 or 16, but 17 works. 18 doesn't. And 19 works. So there's 1, 2, 3, 4, 5, 6, 7, 8 out of 20. Okay, so that's for the first one. Okay, it says 3 tickets are drawn from the hat without replacement. Determine the probability that all are prime numbers. So we got 8 out of 20 times. So now that on the first one you've taken a prime out already, so let's say it was 13. So now you have 7 prime numbers and 19 tickets left. Okay, so let's say the second one was 5. So then the third one, there's only 6 primes left out of 18 total. And that is going to give us our percent. So let's figure that all out. That's a little bit trickier one. So 8 times 7 times 6, 336 over 20 times 19 times 18, which gives us 6840. Right, and so let's see, we could do 336 divided by 6840. When you get such a big number like this, it's just easiest, I think, for the most part, to do percents. So we get 4.9%. 4.9%. All right. On there, you could turn this into a fraction if you really wanted to. So to do that, you would do math, and then you want to turn your answer into a fraction. So we do enter, and it's 14 over 285, or 14 over 285. Okay, so you want to give your answer either as a reduced fraction, a percent, or you could leave it as a decimal. So really, I guess you could also have or 0.049. Any one of these 3 answers work. All right, you should now be able to say that I can distinguish between dependent and independent compound events and find the probability of the events. Okay. If you have any questions, please ask. Thanks.